Hello everyone, I am Raghunath Reddy Madhareddy. The title of my presentation is A Constant Factor Approximation Algorithm for Red Blue Set Cover with Unit Disks. Let's look into the definition of the problem, Red Blue Set Cover with Unit Disks. In this problem, we are given two sets of points. Say R is a set of red points and B is a set of blue points. And we are also given a set of unit disks D. The goal is we need to find a sub-collection D prime subset of D such that the disks in D prime cover all blue points in B and cover the minimum number of red points in R. First, Chan who proposed the geometric variation of the red blue set cover problem access parallel unit space, and they proved that the problem is NP hard, and they provided a polynomial time approximation schemes for the problem. For the case of red blue set cover with unit disks, one can easily extend the reduction of Chan and Hu which they gave for the unit squares, and one can show that the problem still become NP hard for the unit disks also. And however, no approximation algorithm is known for red blue set cover problem with unit disks. The main contribution of our work is the first constant factor approximation algorithm for the problem. We obtain this by considering a special case called as line separable red blue set cover problem. In the line separable red blue set cover problem, all blue points lie below a horizontal line and all disk centers lie above the horizontal line, but the red points can lie anywhere on the plane. Next, we consider another variation of the problem called as strip separable red blue set cover problem. In the strip separable red blue set cover problem, all blue points lie inside a horizontal strip and the disk centers lie on the both sides of the strip, but red points can lie anywhere on the plane. We give a two-factor approximation algorithm for this strip separable case. Let us start with the polynomial time algorithm for line separable case. Let O subset of D be an optimal solution for the given instance of the problem. First, we define the term lower envelope. The lower envelope of a set of disks is defined as the union of the boundaries in the region L minus. There are two well-known properties about the lower envelope of disks in the optimal solution WAOA. First property, every disk in WAOA contributes to the lower envelope. So here there is a disk with a shaded region with a dotted boundary, and it is not contributing to the lower envelope, which means the set of all points, blue points covered by these disks are also covered by other disks in the optimal solution. So such a disk is not required in the optimal solution. Second property, further, every disk in WAOA covers a unique interval in the region. This is true because of the centers are above the line, and these arcs are belongs to the lower half of the disks. Let D1, D2, so up to D mod WAOA be the ordering of disks in WAOA with respect to their appearance on the lower envelope from left to right. We also define upper envelope of the disks. So this is the upper envelope of the disk that is given in the black color. Okay, but however, the upper envelope may not satisfy the properties of the lower envelope. You can see that the disk D3 is not contributing to the upper envelope. Okay, so the first property of the lower envelope is not satisfying for the upper envelope. Similarly, because due to the fact that the disk centers are above the line, so a disk may not completely cover a unique interval. Okay, so that is the problem with upper envelope. Now let us establish some terminology. When as every disk is intersecting a line exactly twice, we call the left intersection point as L of dA for the disk dA and R of dA for the disk dA. Similarly, L of dB and L of R. So any two disks can intersect at most two times, either 0 or 2 times in fact. So we call those intersections as PA1, PAB1, PAB2. And if two disks intersect twice above the horizontal line L, then it forms a region given in the shade, pink color, which we call it as a hole. Okay. Now the important term is a block. A block is a contiguous subsequence di plus 1 so on up to dj of disks from optimal solution O such that the regions in L plus covered by these disks, intermediate disks, lies completely inside di union dj union hij intersection L plus. In other terms, it is said to be a block. The contiguous sequence is said to be a block if the region covered by these intermediate disks on the L plus region belongs to either di or dj, or it may be from the whole. So figure A is a block, but figure B is not a block because there exists a disk with a dotted boundary which is covering some region in the L plus region which is not belongs to di or dj or even to the whole. So there are four different types of blocks that can exist. First type of block is type A, where dA and dj will not intersect or do not intersect. Sorry. So in this case, when dA and dj are not intersecting, this j will become I plus 1, which means the two disks will be adjacent disks in the upper envelope and as well as the lower envelope. Second, the disk dA and dj intersect exactly once above the line and once below the horizontal line. In that case, there is no hole. The hole will be empty. Third case, dA and dj intersect twice above the line, horizontal line L, and it is forming a hole. But however, there exists a disk, you can say this disk, and which is completely covering the hole. So then we call that type of block as a type C block. The last type of block is type D. As in type C block, disks in dA and dj intersect twice in region L plus. However, unlike in type C, there exists no disk d prime belongs to di plus 1 to dj minus 1 such that d prime completely covers the whole hij. We also claim that no disk in di plus 1 to dj minus 1 intersect RDI line segment RDI LDJ twice. So with this, we can partition the set di plus 1 up to dj minus 1 into two sets, O1 that is di plus 1 to dk prime and O2 dk prime plus 1 to dj minus 1, where dk prime is the rightmost disk with rdk prime on segment rdi ldj. Based on the behavior of disks in O1 and O2, we categorize type D block into D1 and D2. In type D1, the first property is the disk dk prime plus 1 completely covers the region dt intersection hij for all disks dt belongs to O2, which means the set of red points inside the hole which are covered by any disk in O2 are also covered by the disk dk prime plus 1. Okay, and the second property, which is talking about the disks in O1, there exists a subsequence dx1 dx2 so on up to dx mu such that every set oxt plus 1, which is the set of all intermediate disks between dxt to dxt plus 1, forms a blocks of type B. Okay, further, no point in dxt minus is covered by dx1 union dx2 so on up to dxt2, which can be captured in the figure here. That means, so these are all the set of disks in O1. Then the disks, blue disks, will actually form upper envelope inside the hole. Okay, and these disk forms type B because every two disks are intersecting, once in the region above and once in the region below the line. And type D2 block is symmetric to type D1. The rules of D1, O1 and O2 switches. The main theorem of our algorithm is block decomposition theorem. It states that let d sigma 1, d sigma 2, so on up to d sigma k be the disks in which they appear on the upper envelope, ordered from left to right. Then the following are true. For 1 less than x less than y less than z less than or equal to k, d sigma x intersection d sigma z intersection L plus is subset of d sigma y intersection L plus. That means any three disks on the upper end, contiguous disks on the upper envelope, the intersection of the first disk and the last disk must be contained inside the second disk, in the middle disk. And similarly, for 1 less than kappa less than or equal to k minus 1, the set O sigma kappa and sigma kappa plus 1, that is d sigma k, that is all the intermediate disks, forms one of the four types A, B, C, D. Okay, so this is the example that is given here. So we use this theorem to design the algorithm, and for the lack of time, we are not going to the details of the proof. Let's move to the algorithm that is based on sweep-line method. We give the sweep-line based dynamic programming method, which returns an optimal solution O in order big O of n power 14 em time, where n is the number of disks and n is the number of points. We first note that by block decomposition theorem, once we know the subsequence of disks forming the upper envelope, the hardness lies in finding the optimal blocks of type A, B, C, and D between pairs of consecutive disks in the subsequence. We call this problem as the block red blue set cover problem. From the first property given in the block decomposition theorem and by the properties of disks in the optimal solution, a red point covered by an optimal solution of a block cannot be covered by a disk in the optimal solution of another block except the points covered by the left and right disks of the block. So the block red blue set cover problem defines like this. We are given two special disks, D left and D right. Okay, and we are given two coordinates, x coordinates, x is equal to s1 and x is equal to s2. And we are also given a set of disks, call it as dp. The goal is we need to find db prime. We need to find a set dp prime which covers all blue points between x is equal to s1 and x is equal to s2, which are already not covered by d left and d right. And second thing is d left comma d right union db prime, that is the solution of the block, which the union of all these disks should form a block. of any time. And third is appearance of every disk in dB prime in region L minus is between x is equal to s1 and x is equal to s2. So then the cost of the solution dB prime is equal to the number of red points covered by the disks in dB prime, which are already not covered by disks d left and d right. So the goal is we need to find the minimum cost dB prime. The snapshot of the sweep-line position is captured in this way. Okay, suppose this is the sweep-line position, and always the sweep-line is placed at intersection of the two disks in the region L minus. Okay, so suppose this green one, D previous and the D current, these are the disks, but it might be the situation these two are completely covered by some other disks in the type D block. This figure is representing type D block because which is actually a crucial one. Okay, so suppose there are two disks, D upper previous and D upper current. So these are all actually forming the upper envelope on the inside the block. Okay, so for us this sweep line we need to remember D previous, D current, and D upper previous, D upper current, as well as one extra disk that we required, because if it is a type D1 block, so we proved the block decomposition theorem states that from O2 there exists one disk which completely covers all the red points which are covered by any disk in the O2. So to avoid double counting, we need to remember one extra disk called as a D extra. Okay, so the snapshot of the sweep line position is captured in a phi tuple D previous, D current, D upper previous, D upper current, and D extra. And we say a phi tuple is a valid tuple if it satisfies these properties, that is L of D upper previous is less than or equal to D L of D previous less than L of D current and less than or equal to L of D current. And the intersection point of D previous D current in region L minus is between x is equal to s1 and x is equal to s2. Okay, and third is this is the property that we are capturing. D preview union D current intersection L plus is subset of union of these five disks intersection L plus. Okay, so that these red points covered by D pre1 D current are not double counted again. So now we construct a DAG, the directed acyclic graph G. The collection, the vertices is the set of vertices is the collection of all valid phi tuples. Okay, now next we construct edges. Let's consider the vertex V, D pre, D current, D upper pre, D upper current, D extra. There are two situations. One is D current may same as the D upper current, or D current may be different with the D upper current. So in this case, D current and D upper current are two different disks. So then we put edge to the another vertex V1, which is of D, instead of D previous it will become D current, and D instead of D current it will go to D new. Okay, and all other three other vertices will be same. And here, what is the D new? So D new is the disk which is coming up in the next envelope. We can guess it. It's a guess. So the total weight that we will give is the number of red points covered by D new which are not covered by any disk at V and D left and as well as D right. In the second case, D current may be same as D upper current. In this case, we required something different. So D preview will become D current, okay, and D current will become instead of D current, some new disk will come, and D upper current will become D upper preview, and another new disk will come D upper new. So therefore, total two new disks are appearing into the vertex, and we place the weight appropriately. Easy to see that the total number of vertices in the graph is order n power 5, big O of n power 5, and from each vertex there can be at most big O of n square possible edges. So the total number of edges in the graph is big O of n power 7. Further, to check the validity of each possible edge and finding its cost, we require big O of m time. So therefore, the total graph can be constructed in or big O of n power 7 m time. And one can easily notice that the graph is also a directed acyclic graph. And one can easily add two special vertices S and T, which can be seen as a source and destination for this directed acyclic graph, to make sure that there is a unique source and sink with the appropriate edge weights. And the lemma that we claim that the cost of shortest path from S to T is equal to the cost of an optimal solution to block red blue set cover problem. Then we have a theorem that one can compute the optimal solution for the block red blue set cover problem in order n power big O of n power 7 m time. We use this as a subroutine to find out the solution for the line separable set cover problem. So now we solve this special case. So here we know that d left and d right are given to us. So now we construct a new thing, a new graph G, which consisting of four entities, is a four tuple d left, d right, s1 and s2. And we put hedges between v and v prime if and only if this s1 prime is compulsory greater than or equal to s2 and the d right is common in both disks, both vertices. And the cost of this edge is equal to the optimal cost of this block, okay, between d left and d right and all, that is covering all the blue points, plus the number of red points covered by d next, which are not covered by d right. So from this one can observe that the total size of the graph is order n power 14 m, okay, because of the block changing, and one can compute the solution in this much time, or big O of n power 14 m time. The correctness follows from the argument that as d left, d right and d next are the three consecutive disks. So if d next and d left are containing common points, those will be completely contained in d right, so there will be no chance of overcounting. Now we move to the strip separable case. So we can see this strip separable case as running two sweep lines parallelly, okay, with same speed. So as we have a polynomial time for L1 and a polynomial time for L2, two line separable problems, but there is a thing that there can be some red points which can be counted two times. When we run the two sweep lines with the same speed, then we may lose a factor to approximation 2. So that's why we obtain two factor approximation for the strip separable problem. Then the next thing is we give four factor approximation algorithm for the problem when all blue points are lies in a delta cross delta box for delta is less than half. This is this is on the same lines of Ambul et al., who give constant factor approximation for the general set cover problem. So the result is you are given set of points and set of disks, okay, geometric set cover problem, inside where all points are inside a rectangular box of size delta cross delta, where delta is less than half. For this problem, Ambul et al. Give a two-factor approximation algorithm. So the main result of Ambul et al. Is, if you are given an optimal solution, By selecting a constant number of disks from WAOA, this constant is not bigger, it is less than 5 or 6. Okay, one can partition the set of points which are not covered by the selected disks into two disjoint strip separable cases. Okay, and for the set cover strip separable problem, there is a polynomial time algorithm is known, so original problem is losing factor 2. Now we follow in the same lines. We also follow the same line, but the case is our strip separable algorithm has factor 2 algorithm, not a polynomial time. So we get factor 4 approximation algorithm. Finally, we use this 4 factor approximation algorithm as a subroutine to obtain 368 factor approximation algorithm for the red blue set cover problem. The idea is partition the plane into delta cross delta boxes for some small delta less than 1/2. Solve red blue set cover problem for each box independently by using the above 4 factor approximation algorithm and take the union of all those things. One can note that a red point R can be covered by solutions of a box of size delta cross delta only if the box is completely contained inside a circle of radius 2 plus square root of delta centered at R. So by calculating for a small delta is equal to 0.999/2, we can conclude that R can be covered by solutions of at most 92 small boxes. So therefore we lose 92 for each small box, we lose 4 factor. So total a red point can be counted at most 368 times. So we lose a factor 368. So finally we got a constant factor approximation for the problem.